back to our final video on hierarchical linear models. Before we jump into R, let me just give a brief overview. We use mixed models or hierarchical linear models when we have non-independent data. And that might happen because you have the same people measured more than once, or it might happen because you have clusters like husbands and wives, brothers and sisters, or a bunch of students within the same classroom, or a bunch of patients within the same therapist. And when we're using mixed models, we have fixed effects and we have random effects. Fixed effects represent the average effect across all groups or all clusters. The random effects are the deviation of each individual group from that fixed effect. And you can choose whether to model something as a fixed effect only or as a random effect, which there is going to be a fixed effect, but you're also modeling the fact that it deviates from that fixed effect. And again, here's a visual to represent that. The solid black line is the fixed effect, and these schools in this case differ from the fixed effect. And this is a random slopes and intercept model, although the slopes look pretty parallel. And once we have fit these models, we can compare these models and see how much proportion of the variance is explained. We could explain the variance at the individual level, which we call the residual variance. We could explain it at the group mean level, which we call the intercept variance. Or we can explain it at the group slope level, which we call the slope variance. And we can use our R-squared estimates to figure out how well our model is fitting, but there's actually lots of other things we can do to figure out how well our model fits. So let me introduce you to a couple other ways we can assess fit. Number one, the intra-class correlation. It actually really doesn't assess fit. I just couldn't think of anywhere else to put it, so it's going here. So what is the intra-class correlation? It is a measure that tells us what proportion of all the variability in the model is due to the cluster effects. So the ICC tells us what proportion of the total variance is due to the clusters. And so if the ICC is 0.5, that tells us that 50% of all the variability in our data set is due to cluster differences. And by the way, the higher the ICC value, that means the more non-independent our data are. So if you see a high ICC, that tells you, yeah, you definitely should be using mixed models. So it's kind of informative. Number two, we can visualize the models, and we can compare visuals across different types of models using compare.fits and visualize. And then we can do model comparisons and use AIC, BIC, Bayes factor, R-square changes we already talked about, and we can use p-values. And we also have the predicted difference. And we also have the fixed effect values themselves. So here's my general strategy, and if you've been following my videos, you know that this strategy is going to seem very familiar because it's very similar to the strategy I've always used. With one small exception, that comes down to the ICC. So the first thing that we're going to do is we're going to compute a baseline model. And the baseline model is just a random effects ANOVA. We don't have any predictors whatsoever. We just allow the intercepts to vary. And the reason why we do that is so we can compute the ICC, again to tell us what proportion of the variance is due to the clustering effect. And then after that, we fit our full and reduced model if we are doing a model comparison, which we usually are. Then once we have our full and reduced model, we can visualize the two different models using compare.fits or visualize. And then we could use the model.comparison function to pit the two models against each other. We could also pit them against the baseline model to see how much both of them are an improvement over a model with no predictors. So you guys excited to see this in action? I know you are. So let's get to it.
We are going to begin by requiring FlexPlot, as we always do, as well as LME4, which is the package we use to do the mixed effect modeling. So the step one, like I said, is going to be to fit a baseline model that has no predictors, and we specify that this way. So again, things outside of the parentheses are fixed effects, inside are random effects. We are saying to R that we want to fit a fixed slope as well as a random slope. And then once we fit the baseline model, we can compute the ICC. And look at that, we have 18% of the variance is due to clustering. So 18% of that variability can be explained by clustering within schools. And like I say here, so yeah, mixed models are important here. You could also visualize the baseline model. Not always of interest, but sometimes it's fun to see. And by the way, most of the examples I've showed you before, we've gone plot equals model, and that just does the single plot, but if you leave it at its defaults, it also shows the histogram residuals, SL plots, and if you have a numeric predictor in there, it's going to also show you residual dependence plots. So actually I am going to run that because I'm not looking at the diagnostics right now, although you probably should. And I should set a good example and actually evaluate those, but I'm not going to right now. So here are three randomly chosen schools, schools 6074, 9225, and 8531. And we see there are some deviations of those schools from the fixed effect, although they're not huge deviations. And we could also run it again, just look at 3 new schools, and run it again. Nice. Now that we've done the baseline model, we want to look at our substantive models. And so let's say that our substantive model, and it's stated right here, let me move it over so I can read it. Do we need to have socioeconomic status have a random slope? So it's a good question. We know we want to put socioeconomic status in the model. Do we want to model it as a fixed effect or as a fixed and random effect? And so if we run those 2 models, we get nothing, of course. Well, it doesn't show us anything, although we could look at the fixed effects, which I'll show you how to do that here in just a minute. And then we can visualize the model, and that's what our model looks like. Very interesting. So to me, now remember this is modeling the random slopes. So despite the model saying that these slopes could be different, those slopes look really parallel to me. Let's go ahead and run it again. Look at 3 new schools, and those look pretty parallel to me. So that's kind of interesting. So I'm thinking that, so far at least, there's evidence that suggests that we really don't need that random effect in there. So here what I'm going to do is I'm going to use the compare.fits function. And so I'm going to visualize the 2 models, one where it has a fixed slope and one where it has a random slope. And make this bigger. The red line is the fixed slopes model, and the blue line is the random slopes model. And these red lines should be exactly parallel to one another, although they may be different in their intercepts. And that seems to be the case. And notice that the blue lines, because again, we're allowing the schools to have their own slopes, and so not surprisingly, some of these slopes are slightly different, but they're not that much different. And of course, that only shows 3 schools. We could look at more than 3 schools if we wanted. And so to do that, you can just type in clusters equals and then whatever number you want. We're just going to look at 10 here. Probably going to be a big plot because it's got a panel on 10 variables. So if we let that refresh, we see that across these 10 schools, for the most part, the 2 predictions look pretty similar. So that, again, further evidence to me that we could probably just model the socioeconomic status as a fixed effect. And we could supplement our visual analysis with some statistics. And before we do that, we might want to compare the fixed slope model to the baseline model, just so we could see how much variance is being explained by socioeconomic status as a fixed effect. And it says relative to the baseline model, which again has no predictors, we are explaining 5% of the variance-ish. So the lines are closer to the individual dots. And then our intercept, we improve that by 44%. So we explain 44.6% of the variance in intercept variance. Basically what that means is that the intercepts are on average going to be closer than the fixed effect than they were before, which is good. And so once we do that, we could also do the same thing with the random slopes model. And these are actually comparable. So I'm gonna scroll down so we can look at these simultaneously. So before, we explained 54-ish% of the variance with just a fixed slope. And now if we have a fixed and a random slope, we now explain about 60% of the variance. So we improve, I'm sorry, not 60%, but about 6% of the variance. So we improve by 0.004-ish. So not a huge improvement. And likewise for the intercepts, we started at 0.446 and we actually got worse, and that can happen sometimes. That's the change in R squared, but really what we want to look at is we want to look at the fixed slopes versus random slopes model. That's really the substantive question that we wanted to compare. Unfortunately, these models are nested, so we can get a p-value, and according to the p-value, it doesn't meet the standard 0.05 threshold. According to the p-value, we would say that we marginally retain the fixed slope model, because that's the simpler of the 2. But the Bayes factor actually tells something quite different. It says there is striking evidence in favor of the fixed slope model. So they both technically agree that we favor the fixed slope, but the Bayes factor is much less ambiguous than the p-value was. And then the BIC favors the fixed model, and the AIC actually favors the random slopes model, which is interesting. So we don't have 100% agreement here. But I'm inclined to say let's go with the fixed model since it's the simpler model and we do have the majority of our estimates saying that we ought to favor those. And then here are the predicted difference. So I guess if we could make our plot a little bit bigger just to identify what the scale of math achievement. And so that's actually interesting. So it's saying that the maximum difference in the two models and predictions is only about 2 points. Which again suggests that we are needlessly complicating things by adding a random intercept. And then here's the R-squared change. And so remember the baseline in this case is going to be the simpler of the two models, so that's going to be the fixed slope model. So we actually lose explain variance when we add a random effect for the residuals, and we explain a little bit of intercept variance, but not a lot. So all this seems to, not all of it, but the majority of it seems to say that we ought to favor the fixed slope model, and that's what I'm going to go with. Now at this point, and one thing I didn't do in my notes before is it's actually probably a good idea to study what the fixed effects are. So to do that we can go summary fixed underscore slopes, and if we run that then we get these estimates, which we've seen some of these before. These are the residuals, which I don't spend much time looking at. I don't spend much time looking at the random effects. These are just the variances. And here are the fixed effects, and those are the things that are really of interest. So intercept of 12.65, what does that tell us? That tells us that when one's socioeconomic status is 0, which I believe is equal to the mean. Let's see if it's centered on 0. So if we look at this much bigger, boy, that font is making it hard. Well, it's not the font, it's the number of panels we have. So it looks like the socioeconomic status might be approximately centered on 0. So, and I'm guessing it is. So that's basically saying that the average math achievement for somebody who is of average socioeconomic status is going to be 12.67 on this 0 to 25 scale. And it tells you every time you increase by a standard deviation in socioeconomic status, we expect your math achievement to increase by 2.39 points. So that's interesting. Maybe in a future version of FlexPlot, I will also have standardized estimates. These are kind of half standardized. They're standardized according to X, but not according to Y. So maybe you could look forward to that in a future development of FlexPlot. So that was interesting. We determined that the fixed slopes model is better, probably. We don't really need random effects there. They all seem to be pretty parallel. And now let's say that we have a separate research question that we want to look at minority status and ask whether inputting someone's minority status helps us improve our fit above and beyond what we get through socioeconomic status. And so I'm just going to run that model right there. And then as before, I can visualize the two models, but now it's going to, oh, you know what? It's doing the random slope. So I'm going to do because that's the model that we ended up choosing. And by the way, remember that categorical variables generally have fixed effects, and that's what I modeled here. If I wanted to, and if I wanted to spend more time on this, I could model it as a random effect and do another model comparison, but we're just going to stick with this. And so what we're looking for here, again, is we're trying to see if the predictions are vastly different, or even not vastly different necessarily, but meaningfully different. Remember, each of these lines represents the prediction from the fixed slope model versus the minority model. And what you would expect to see is that the red line is exactly the same across the two of them, because the fixed slopes model doesn't have minority as a predictor, and so they should be identical. And so what you will see is that you will see the blue line, and the blue line, on the other hand, will explicitly account for minority status. So the blue line over here says it is predicting, relative to the other model, it's predicting slightly lower scores for minorities and higher scores for non-minorities. And likewise down here we have for school 2639, they're pretty similar. On the other hand, for no minorities, which this school doesn't actually have any minorities, so I don't know that we trust those predictions anyway, but if it did, it would say that we expect the minorities to score, or the non-minorities, I should say, to score, I don't know, looks like on average maybe 3 points higher. And down here again, we see that for this school, there's not many minorities, and you would expect to see a So for the minority model, we are seeing lower predictions than the one that doesn't account for minority status, and then they're about the same for those who are not minorities. That's how you would interpret those lines. And so in some situations, like right here and right here, the two differences aren't that big, but they're a little bit bigger for this school and for this school and this panel. So at this point, I'm inclined to say that there may be a minority effect, but it's hard to tell. In fact, let me run it again and see if there are schools that show a whopping difference between the two. There we see much bigger differences in prediction. And we'll go ahead and do another one just for fun. So at this point, I'm a little unsure what to make of it. It could go either way in my opinion. So let's go ahead and look at a model comparison and run that and use some statistics to help us out in making our decisions. That's kind of interesting. So our visuals were a little ambiguous. Of course, we could only look at a few schools at a time, but the statistics are less ambiguous. And the reason why these statistics are less ambiguous is because there is a massive sample size in this data set. We're only looking at a few schools at a time, but if I remember right, there are thousands of schools. And so across thousands of schools, it's consistently estimating a difference between the minorities and the non-minorities. Because again, the Bayes factor favors resoundingly the minority model. And likewise, the p-values say the two models are different, and if they're different, then it's always going to go with the more complex model, which in this case is minority. And the BIC, what does it favor? Yep, it favors a minority, which, by the way, the BIC is always going to favor the same model that a Bayes factor is going to favor, because the Bayes factor is just a function of the BIC. And then the AIC, it is also resoundingly favoring the minority model. And then now we have the predicted difference between the two models. The biggest difference that it could detect across all predictions was a 3-point difference between one that doesn't account for minorities and one that does, but on average, or on median, it is predicting about a 0.4 point difference, which isn't a big difference, but again, with such a large sample size, it has no trouble determining that this is not noise. And then now we got the R-squared change. So again, the denominator here is going to be the baseline model, which in this case is, oh, and you know what? I'm looking at the random slopes model. Let's go ahead and do the fixed slopes. So let's just pretend I did that whole entire interpretation with the fixed slopes. But the numbers end up being pretty much the same, which is what I would expect, because before we couldn't really tell a difference between the fixed and the random anyway. Yeah, relative to the fixed slope model, we are explaining, 3% of the variance, 3% of the unexplained variance in fixed slopes is now explained by minority status, and 17% of the variance in the intercept is now explained by minority status. So those are respectable, I'd say. And then now that we have a final model, let's go ahead and look at the estimates, and to do so, we can go summary fixed underscore slopes, and sorry, not fixed slopes, minority. And if we do summary of minority, we can now, again, I just jump straight to the estimates. I don't need these numbers to tell me what the visuals see. I think those aren't inherently interesting, so instead I'm just going to look at the fixed effects. And so now the fixed effect of the intercept is 13.5, which again tells you if you are of average socioeconomic status, we expect your math score to be about 13.5. And then for every standard deviation you increase in your socioeconomic status, we expect your math score to increase by 2.13 points. And then now we really get to the variable of interest, the minority yes variable. And so what is that telling us? At negative 2.97. So we know minority is the variable, and then yes tells us what level we are comparing. So relative to those who are no minorities or non-minorities, the minorities, or those with minority score of yes, have a negative 2.9782 difference in their math achievement scores. Or to put that in a less confusing way, we see about a 3-point difference between minorities and non-minorities, with the minorities scoring on average 3 points lower.
All right, wasn't that fun? So now let's go ahead and review our learning objectives. Number 1, what is the ICC and what does it tell us? So again, the ICC is the intra-class correlation, and it tells us what proportion of the total variance is due to clustering or non-independence. Number 2, the general strategy for modeling mixed models. 1 is to fit a random effects model. 2 is to compute the ICC. Number 3, fit a full and a reduced model. Number 4, visualize the two models primarily using compare.fits. And number 5, compute statistics using model.comparison. And I should probably add to this now, number 6, study the estimates. And in this case, I mean the fixed effects. And third learning objective, what are the estimates of interest? So we have the AIC, the BIC, the Bayes factor, the p-values, the predicted differences between the two models, and of course the values of the fixed effects themselves. So with that, that concludes our mixed model discussion. Next, we're going to talk about generalized linear models. So until then, peace out.